we have this part loaded in here. Typically parts have extension .sldprt as you see it.
Okay. Mm-hmm.
Now your visual cam interface shows up as a tab in the command manager. So this bar up at the top is called the command manager in SolidWorks. You could create
Okay.
sketches, you could extrude, create solid modeling. So these are the different tabs in SolidWorks. Now, and the
Okay.
Visual Cam's interface shows over here on the left pane. You can resize the feature manager tree over here
Mm-hmm.
to view all of the commands under the machining browser. So the machining browser and the machining objects. Now, the interface looks very similar to what you've used to in our CAM plugin for Rhino.
Yes, I am totally sure of that. I am watching that right now. It looks pretty similar.
Mm-hmm. Okay, so now if you go over to the feature manager design tree, this shows all the features, how the part was designed, the feature tree in SolidWorks.
Okay. Mm-hmm.
And if you click on the Visual Cam tab, you will see that the CAM interface shows directly inside of SolidWorks.
Okay.
Okay, so the typical workflow here is you go over to the Program tab and you define the machining process.
Mm-hmm.
Now there's an additional tab that shows up in SolidWorks, our plugin for SolidWorks, which is not typically common in the standalone or the plugin for Rhino, because in Rhino and in Visual CAD you can rotate the part around easily.
Yeah.
In
Mm-hmm. Mm-hmm.
SolidWorks, it's modeled parametrically, so you got to insert a feature in the tree if you need to rotate the part. So rather than rotating the part, it is easier to just rotate the coordinate system for machining. Now, you got to define your initial orientation. Now, by default, Visual CAM uses the same orientation as the world coordinate system that you have in SolidWorks. Your Z-axis is in the same orientation as the machine coordinate system, Z-axis, and then your X and the Y.
Mm-hmm.
Now, if
Okay.
for any reason you want to start by setting the Z to be normal or perpendicular to this face, then you can establish this by changing. Rather than having to rotate the part in SolidWorks, you just rotate the coordinate system in here, where I can choose to rotate it, so I can put the Z to be normal to this particular surface.
Mm-hmm. I understand. Okay.
So this is one of the key differences between our RhinoCam or Visual CAD CAM standalone versus the plugin for SolidWorks. So you
So.
establish, rather than rotating the part and moving it to
Mm-hmm.
the origin, you would use the Machine Tool Coordinate System tab to basically align the coordinate system for the XYZ orientation of how you're going to be placing the workpiece on the machine tool.
Mm-hmm. Okay. We don't. I mean, in SolidWorks, we don't rotate the part, the model, but we use this tab in order to rotate the coordinate systems of the software in order to match the orientation with our CAM.
That is correct. You're absolutely right.
Okay.
Now
Okay.
also you have the option to establish the origin. So typically for 5-axis machining, you would establish the initial orientation and an origin, and all of your toolpaths would be computed based off the initial orientation and origin. Now again, the origin is by default set to where the origin is in SolidWorks. So if you go over to the feature tree, you'll see that the origin is right here. This origin in the tree points to where the origin is, where my cursor is on the model. So by default, that's the origin location, but you can change it. If you want to move the origin to a different spot, you can hover the mouse and cursor pick, and you can specify it, you can pick a point. So this will change the XYZ0 origin. So again, rather than moving the part to XYZ0 in your CAD that you typically are familiar with doing it in Rhino or in the standalone product, in this particular setup, you just pick where the origin needs to be. So you establish that.
Let me ask you a question. And that origin would be represented by the G54 when we start to create the program, or
Yes. If you're
yes, yes.
programming a 3-axis machining operation, you could add a work zero to establish the origin.
Mm-hmm.
So in the case of 5-axis machining, you
Mm-hmm.
want to make sure you establish your initial orientation and origin, because all the toolpaths will be computed based off this origin. So when you post it, everything would be computed based off this origin. Now, if you're just
Okay.
programming a normal 3-axis operation, after you establish this XYZ orientation, you pick OK to accept it, and then you can create your stock and insert what is called a work zero, which allows
Mm-hmm.
you to establish the orientation for it. So you can then add a work zero and choose where you want to place the origin. And this could be your G54 or G55, whatever the work code and offset is.
Mm-hmm.
So
Yeah,
this
but
would be the
this is
typical case for 2 and 3-axis machining.
for
Now, in the
access.
case
Yes.
of 5-axis machining, even if you place your work zero over here and your initial origin is defined over at this point right in here, right?
See, I'm sorry, it's so loud. I'm sorry. Yeah.
So
The
when you post-process toolpaths in 5-axis, you have this option to output all coordinates in local orientation or transform them back to the world. So typically in 5-axis machining, you would want to transform this back to the world coordinate system origin. And that's why it'll transform it back to the initial origin and not just to the work zero. So that's the reason why when you do 5-axis indexed or 5-axis simultaneous programming, you would want to establish your initial orientation, because even though you add a work zero, it'll first still go back and transform it to this position.
Mm-hmm.
Okay.
Yeah, and that is so important. That's the reason, because it's so important to write, choose this position
Correct.
at the beginning of everything, all the process.
Right, because there's only one origin that you typically reference out of when you do 5-axis programming.
Now, normally when you just turn on any machine, you know, the machine by itself runs a small program for make a quick run, all the X, all the Y, all the Z, and return to the machine home. I'm not sure if you know that. I'm pretty sure that yes. It's like called home or house machine. That origin of the machine by itself is related with what? With the UCS of the SolidWorks, or is related with this coordinate or origin that you are showing me right now?
So by default, the orientation is same as the orientation of the coordinate system in SolidWorks, and the origin is at the origin in SolidWorks.
Yeah, okay. By
default,
recognize
yep,
and
by
match.
default, yes, and match it. Now, typically users may not be using this orientation or origin when they design the parts and when they create the drawings, because they're probably not taking into account that, you know, how it's going to be machined, because the design engineer is not aware of how the CNC programmer or the user is going to machine it. So that's the reason why you have all of these nice controls in here to establish the orientation and also establish the origin.
Okay.
Okay. Now, if they design using the correct orientation, then you don't have to go through the step of reorienting your coordinate system or the origin in using the Visual CAM's Machine Tool Coordinate System tab.
Okay. So basically, if the engineer doesn't want to be really in deep of this, I can jump and just make sure that the matching is automatically.
Yes.
Right?
Yes.
Okay. Just one question here. Spin angle, this 90 degrees normally make me crazy. What is this? Is the angle for the spinning of the what's the name of spindle? Is 90 degrees because the machine is vertical, and when we use a horizontal machine, I have to set here 180. Is that correct or is a mistake?
This is to change the orientation of your XYZ coordinates, like rotating your coordinates. Now consider you have your gumball in Rhino. Is that right? You're familiar with the
Uh-huh.
gumball, right? So if you want to
Yes.
rotate your coordinate system, so you want the Z to be perpendicular to this surface or this face, you would want to rotate it 90 degrees about the x-axis, right, using the right-hand thumb rule. So if you put in spin angle 90 and click on the x-axis, you will notice that now it's rotating the coordinate system about the x-axis by 90 degrees so that the
Mm-hmm.
Z is perpendicular or normal to this, the front face of the part.
Exactly. Mm-hmm.
So
Yeah.
now you
Okay.
can use these angle, you can specify an angle, and also you can specify you want to rotate X, Y, Z, or combination of these. Now if I want to rotate it to this face, I could do 90 degrees about X, and also I can do a 90 degree about Y. Now the Z axis would be normal to the right side face.
Okay. Because I think that is used in some moment for 4-axis programming when you want to use the turning feature. Is that correct?
When you do 4-axis programming, you're going to do rotate table setups rather than
Mm-hmm.
using
Table
this
setup.
machine.
Yes.
Yep. And you specify the rotation angle about the axis of rotation that you've defined. Okay?
Mm-hmm. Yes. Yes.
All
Yes.
right, so now here we're going to go back and reset it to the world coordinate system, the same orientation. So when we want to start machining this part, we're going to
Yes.
basically place the block so that this feature will be looking down, through the machine tool as you want to mill this. So you have your X, Y, and the Z orientation, and the origin is over at this corner.
Okay.
Okay? Now we established that. Now the next thing we want to do is go ahead and define the machine type. So we're going to set the number of axes to 5
Mm-hmm.
and the configuration of the machine tool. We support 3 different configuration types. These are head-head configuration where the 2 rotational axes is on the machine tool head, which means the part would remain stationary on the bed of the machine. The part won't be rotating. The machine, the tool on the spindle would rotate to get to different orientations.
Mm-hmm. Yes. All the A and B movement will, and normally the Z will hold in the spindle in the head, right?
That is correct.
Mm-hmm. Yes. Yes.
We also support machine configuration for table head, where one of the rotation could be like a 4-axis, like an X-axis or Y or Z-axis, and the other could be on the spindle. So a combination of a rotary table and a rotary head.
Mm-hmm. Table A, head B, something like that.
Yep.
Plus
A and B
plus
or
C.
C and B or A and C, whatever the conventions are used for representing the head
Okay.
in the
Perfect.
table.
Yeah. Understood.
We also can support table configuration where the table would be rotating. There would be 2 tables, one on top of the other, like a trunnion. It's also known as trunnion type of machining, where you have 2 rotary
I saw that.
tables, and the part would rotate, and the tool would remain perpendicular to the XY plane of the bed of the machine. So the part would be rotating. So typically, like when you machine like impellers and small parts where it's easy to rotate the part rather than having to rotate the head. So like there are
Mm-hmm.
several machine tools which do trunnion type of machines. So
Okay.
these are the
Trunnion.
3
Yeah.
different configurations. So now you pick a configuration. So we'll go with the standard type of configuration where a head-head. Now if you go to the help section in here, it actually talks about an example of the head-head. So you can see that there's a C-axis which rotates
Mm-hmm.
about the parallel to the Z, and then the B-axis could be rotating parallel to X or Y. So this is called a head-head configuration.
Okay. Understand.
So in the typical case of a head-head configuration, your primary axis will always be rotating about either Z positive or Z negative. So depending on how the machine tool is defined, Z positive or Z negative. So if it's Z positive, you'll see that the Z axis rotation direction is pointing up. You see the green arrow along with the Z axis right here.
Mm-hmm. Yes,
That's
I
the
can
primary.
see
So
it.
if you point your thumb in the direction of the arrow, So if you do a Z positive, if you do a right hand thumb rule, so as you roll your wrist towards you, that would be a positive rotation. As you roll your wrist away from you, it'll be a negative. You can switch between Z positive or Z negative. So depending
Mm,
on which way the machine tool is set up. Similarly, you can also do the coordinate system orientation for the secondary axis. The secondary axis for a head-head machine could either be along X or could be along Y. You can see the red
mm,
arrow here represents the Y positive, or you can have it set to Y negative. Again, this depends on how the machine tool is set up.
mm-hmm.
So you define these two in here, and you can also specify the limits for the rotary axis. Typically, for the primary axis, it could be a no limit, or if you have like cables or something in the way, you may have a limit where it can only go like plus or minus 360, or just 0 to 360 only. So you can specify the limits for the primary axis, or you can even input a user-defined limits in here, minus 3 to plus 360 degrees, for example. It could be possible, right? So you specify
Okay.
the limits for the primary axis. You can also specify the limits for the secondary axis. So in this case, the secondary axis is a head, so the head can go plus or minus 360. You might be only able to go like minus to plus 110 or 115 degrees. So you can specify them as user-defined limits in here, so how far the head can tilt, right?
Okay. Yes, I understand. And I have to check really well the features of the machine in order to set correctly those degrees and those features there
Yeah.
in RhinoCam.
Right. If you
Excuse
look
me,
at your
Visual Cam.
yes, if you look at the machine tool specification provided by the machine tool vendor or manufacturer, they would tell you the rotary axis limits of primary and secondary, and they will provide you with most of the information. And in here, you have a parameter called gauge length. Now, gauge length is required where you have a machine that has a head. Any combination with the head will have a gauge length. Gauge length is the distance from the pivot point that you see right there, where the point about which it rotates, to the tip of the tool. So what you're inputting here is the distance from the pivot point down to the spindle face, and then
Yeah.
tool length that you define in your tool definition is automatically added to it when the gauge length is specified in here. So typically the gauge length is a constant parameter for a given machine tool, the distance from the pivot point to the spindle face, but the tool length would vary depending on how far the tool is, you know, sticking out from the spindle face to the tip. So you put in the gauge length. It could be, for example, 6 inches. I'm using a number here, right?
Mm-hmm. Yes.
Now the gauge
Yes.
length parameter can only be entered when this box is not selected. So if this box is checked, then it's going to output every coordinate system in the local coordinates, like a rotated coordinate system. But when you uncheck this, it'll transform everything back to the world coordinate system orientation. That's what most machines expect in 5-axis, is transform back the coordinates to the world. So in this particular case, if you're milling this particular face, your cutter is moving in and out along the y-axis. If you're cutting on this face, your cutter is moving in and out along the x-axis when you look at it down from the top, looking down from the world coordinate system orientation. So unchecking this box will transform this Z motion into the motion that is in the world coordinate system. Am I making sense?
Yes. Yes. Yes.
Okay,
So
perfect.
that helps to manage just one coordinate system for the whole part
That is
because you
correct.
have. Okay, I understand. I understand.
All right, so now you define the machine tool. The next step is to create your stock material. So when you pick stock, box stock, this will compute the length, width, and the height, very similar to how you define your stock for 2 and 3-axis operations. Okay?
Mm-hmm. Mm-hmm.
Now also, by default, the setup coordinates is automatically oriented to the machine coordinates. So whatever you define in here is inherited automatically by the initial setup coordinates.
Okay.
Okay, now we want to go ahead and create the toolpath. So I'm going to start out with a toolpath in here. So I want to do a roughing operation. I could choose 3-axis or a 2-axis operation. I pick roughing. I can now select my geometry for roughing in here. I could say I would like to keep the cutter completely inside this area, so I can select a chain of edges or I can do select tangency or select loop. These are the selection tools that are offered in SOLIDWORKS where you can automatically do a chain of edge selection, similar to how you can use in Rhino, like using the chain command to select chain of edges. And then
Yeah.
the workflow is very similar. The interface looks very similar as you see it. You specify your tool, you set your feeds and speeds, you establish your clearance, you specify
Yeah.
your cutting parameters right in here, you can specify your cut levels, and then you hit generate, and this will automatically establish your toolpath. So there's your
Okay.
roughing toolpath for the top orientation. Now you can go ahead and run a verification, and you'll see that the roughing toolpath is being simulated right in here.
Cool. That part is really clear for me. It's no problem. I manage
Mhm.
that. It's okay.
Right.
Hmm.
And now you can go from a roughing operation to a finishing operation. You could program a horizontal finishing, or, we could do a 2D pocketing, depending on the type of operation you'd like to program. You specify the cutting parameters in here, and you click on generate. So this would produce a finishing toolpath around those areas.
Hmm.
So since you're familiar with how to program your toolpaths, I'm not going to spend a lot of time on this here. Again, if you want to do a pocket or drilling, you can drill or pocket these holes. Now once you're through programming this top face in here, let me go ahead and just add a drilling too. So we'll just do a drilling, and we'll say select holes on this particular face. We'll pick that. We'll go grab a tool for it, and then we can specify a depth so you can measure or pick the depth from the face. And
And
the depth
once
is
I remember that you tell me that it depends of what kind of a strategy for drilling, the machine, the software will create some of those scan cycles, no, that I think it's G78, something like that.
G81, G83, yes,
Exactly.
it creates CAN cycles. Now with our 2017 version, we've introduced an option to output them as linear motions. There are several machines which do not support or handle CAN cycles. So when you select output as linear motions in version 2017, we automatically convert these to a linear motion. So rather than outputting them as a CAN cycle, it'll output as a linear motion.
Okay.
Okay, so now we programmed from the top orientation. Now you want to go ahead and program it from the sides. So the way you would program it here is this is how you would start programming indexed 5-axis or positional. So you go ahead and add a new setup by going to setup under the program tab, and you click on setup, and this will allow you to change the orientation from which you want to machine. So now I want my tool to be able to cut these pockets, so I need to change the orientation. So I could rotate it. In this particular case, I could say perform a 90-degree rotation in here, so the tool would be
Mm,
normal to the surface. Or if you're not sure what the rotation angle is, you can use select the surface, and I can just pick this face in here, accept it, and you will see that now the z-axis is oriented based on the surface normal. Now if you need to flip the normal on the
flip,
surface,
exactly.
you can
Uh-huh.
go ahead and rotate it in here by using the controls. I can rotate the coordinate system right in here.
Mm. So I press Control and make a click and specify in the axis that I want to flip.
Absolutely. You click on the axis
Mm.
that you want to rotate about. So
Okay,
now
cool.
you'll notice that your coordinate system is rotated. The setup 1 was parallel to the top face. Now the setup 2 is parallel to the front face.
Ah, okay, good.
Now you
Okay.
can add operations, very similar to how we program it. So I can repeat the same roughing operation. I can copy it from one setup
Mm,
down to the next setup in here. I can make edits, make
yes.
changes. I can also specify cut levels and say this is how far I want to go. So you'll notice that your cut levels, your clearance plane are automatically oriented
Oriented.
in the same orientation
Pre-orientation.
as the
Yes.
coordinate system.
Mm-hmm.
And now you pick generate, and this would produce your
Wow.
roughing toolpath for the
Wow.
new orientation, and you can run a verification in here.
Mm, yeah. And
So
we make that in an indexed way, right?
index,
We need to
yes, index,
turn the part in the machine, and when the moving is completed, the turning is completed, the machining will start.
That is correct. In this particular case, we are looking at a head-head configuration, which means the part would remain stationary, the orientation of tool would change to be able to program from this particular orientation. Now, if it's a
Mm,
table, or a table head, the part would be rotating on the machine.
okay, I
So again, it
understand.
depends on the type of 5-axis machine configuration you currently have or your customer is going to be using.
Mm, okay, okay.
So
And
now, I'm
if
sorry, go ahead.
just for understand, if it's the configuration table head, basically I follow the same procedure, but probably the program at the end will send or will post-process a program, a G-code that manage or handle the continuous movement between the axes.
That is correct. So depending on whether it's a head, or table configuration, the steps that you're going to be doing for programming the toolpaths are going to remain the same. The the
Mm,
output, the computation is automatically handled based on the configuration and the primary and the secondary axis that you define. That's what
oh,
basically takes care of the computation of the angles, whether to rotate the table or to rotate the head or to do a combination of both. If it's a table head machine or if it's a table machine, it'll figure out what angle to rotate the primary and what angle to rotate the secondary axis by. So you don't have to worry about those computations.
cool, cool. So basically, I keep working as between quotations as three axes, and the program by itself will handle and manage all these kind of tricky parts with mathematicians and angles and everything.
That is correct. So
Hmm.
we've got through the programming of the setup number 2. Now we can repeat the
Hmm.
same process for setup number 3. So I'm going to now rotate it by to the right face. So I can either use select a surface. I can just pick that face, and you'll notice that the surface
It's
normals, based on the orientation of the normal, it'll orient the
right.
coordinate system. And
We
if you
need
need
we need to flip. Why? Yes, exactly. Okay, good, good, good. Yes.
And then you can repeat a roughing operation, or if you just want to do like a 2D pocket operation, you can program a pocket operation in here. So you could do a 2-axis pocketing. So you could do a combination of 2 and 3-axis operations in here. You can specify the tool. You can establish your cutting conditions in here. You want to go from this face down to the face right here. So the depth is automatically computed based off the orientation of your coordinate system. And you can specify your depth per cut. And then generate would create your toolpath. So this is how you go about programming it from different orientations.
Just one question, my friend, just there in that point. That steps works because the last surface that you selected is flat and also parallel to the external surface. But if it's not flat or is not parallel, it works in the same way?
Well, you need to have a planar surface if you want to use that for orienting your coordinate system. Now, if you have a sculpted surface, then you can rotate it by an angle, maybe like a 45 degree, or so that the tool will be able to machine those features and there aren't any undercuts by looking from that orientation.
Okay, okay. My mouse is not helping to show you where, but no problem.
Yeah, I can give you access for keyboard and mouse, and you should be able to point it to me right now.
Hmm. I was talking, yeah, by here. First, we choose this as reference, right? And then we choose this another surface, and I was talking that this surface is, of course, planar and parallel to this one. But if these have an angle or is sculpted, this procedure have to be different. That
Well,
was my...
you would still be setting the z-axis normal to this particular surface, but then you would program a 3-axis roughing and a finishing
Yes,
toolpath rather than using a 2-axis operation, since the
yes,
floor of the part is not planar. So
was
you would
flat.
have to, or it's in an angle not planar with the orientation. So you would basically have to program it with a 3-axis toolpath.
Will work better. Yes, yes, I
Yes.
understand. I'm sorry. Mm-hmm.
Once you have all of these programmed, you
Mm-hmm.
have your post. We would need to provide you a 5-axis post. We would need to develop one based on a machine configuration. So we can take one of the existing 3-axis posts and we would have to update it to a 5-axis. So once you have it set up in here, right-click and do a post all. Will post and compute the angles for each of these orientations.
Wow. Okay. So that will make easy everything.
Yes, so I'm going to go ahead and show you a sample output in here. So just give me one moment.
Access, but I understand pretty much all your explanation until this point.
Okay, so we've developed several different posts for a variety of different machines. So in this, for example, I could choose maybe a post for a Fager controller in here, like a Fager
The machine
8055
that
or
they have is
right,
Shopbot
ShopBot.
5
Okay, so we do have post for ShopBot in here. We can output in inches or we could output in millimeters. I'm going to select the inch post processor, and I
Okay.
would set the output extension as .sbp. So I would
Mm-hmm.
use .sbp as the file extension,
Mm-hmm.
and right click on the machining job and you pick post all, and this would create your G-code output,
Okay.
and you will notice that in your output the M5 represents a 5-axis motion for ShopBot. So it shows that
Yeah.
for the initial orientation for setup 1, it's at 0, 0 for the ShopBot. So because we are doing the top orientation, and then when you do a search for the next M5 in the program, you'll notice that it's rotating by 90 and minus 90 to get to this setup orientation number 2.
Mm-hmm.
So it's automatically computing the rotations. Now the ShopBot machine is a head-head configuration. So now you see that the angles are being outputted, so it's rotating 180 and then by minus 90 to get to the next side, which
The
is
right position for the next machining.
that is correct.
Mhm.
So it automatically determines the angles for you. So this is how you would go about programming indexed 5-axis operations. So you would create a setup for each orientation, and then you would program 2 and 3-axis operations. Okay?
Yes, understood.
Now the next step we're going to take a look at is programming a simultaneous 5-axis operation in here.
Okay. Okay. Wow. And Shopbot is able to handle simultaneous machining, right?
The ShopBot 5-axis machine tool can handle both indexed and simultaneous. Now it depends on what configuration of visual cam you're using. So if you're going to be using the professional configuration, the professional configuration allows you to do indexed programming only. If you have the premium configuration, then you can also program simultaneous 5-axis operations.
Okay.
So
Professional give you some simultaneous for 4-axis? Yes, I think, right?
professional includes simultaneous 4-axis and indexed 5-axis. Premium
Mm-hmm.
offers simultaneous 5-axis and also indexed 5-axis in addition to
Okay.
4-axis. So it has all the features of professional plus simultaneous 5-axis on the premium configuration.
Mm-hmm.
Okay, so now I have this part that is designed. You could have designed it in Rhino, or you could have designed it in any CAD system you could import in. I also have a stock created in here, stock by a region or an extrusion, as you see it. Now we have a roughing operation program, so you could do a combination of both indexed and a continuous toolpath in here. So there is a 3-axis roughing operation that's programmed, as you see it. And let's go
Mm-hmm.
run a verification. So I'm going to pause simulate to end. So the 3-axis roughing operation has been programmed with an end mill. Now you want to make sure that you have your machine tool defined correctly. 5-axis, head configuration, your primary axis, your secondary axis can be defined right in here. And you can also specify the rotary axis limits for primary and secondary axis. And you can input your gauge length parameter as well. Okay?
Mm-hmm.
Now we have programmed the roughing toolpath. The next step is I would like to program a finishing toolpath, but I want the tool to follow the surface, be normal to the surface. So that's where you can use your simultaneous 5-axis operation. So you go over to
Exactly.
5-axis and you could choose from different types of operations in here. You could start with a surface normal machining. This would be similar to your parallel finishing, or also known as surface parallel machining. So in 5-axis simultaneous, you would actually have to select surfaces for machining. Here I'm going to pick
Mm,
this surface, and this is the surface I would like to program. That's my drive surface. And when you select the surface, you'll notice that the surface is automatically being added under drive surface. It also displays the orientation of the surface normal. So if the surface
oh,
normal is not in the correct orientation, you need to flip it. You can use these controls to reverse the normal orientation of the surface.
okay, okay,
Next step
okay.
is to make your selection for the tool, feeds and speeds, your clearance. You have different ways you can establish clearance for simultaneous 5-axis. You can do a planar, you can do a spherical clearance, or a cylindrical clearance where you can specify the clearance X, whether you want to do X, Y, or Z. You can input all the
Mm,
parameters. Now for this particular process, I'm going to just do a planar clearance definition, and then you set your cutting parameters where you can specify the cut pattern, cut traversal, step over. You have any additional tool access control. You can also do multiple levels. In finishing, entry and exit parameters can be specified right in here. And you can also do a gouge check. So typically in 5-axis, when you select the surface for machining, that's the only surface that's going to be taken into account for programming your toolpaths. But you want to make sure that you don't gouge any adjacent surfaces. So you use gouge check, and so you want to check for gouge against these surfaces in here. So you don't cut into these adjacent surfaces or walls. So you want to make sure you add them for gouge check, and you can also specify what strategy you want to apply for gouge check, whether you want to retract along the tool axis, you want to move the tool away, or leave out the gouging points if there's a gouge that's determined. And now you pick generate, and that'll compute your toolpath.
yeah, I turned off my microphone because that was so loud. I'm sorry.
No problem. So as you can see, the surface parallel finishing toolpath has been generated,
Mm-hmm.
and I'm going to run a verification in here, and you'll notice that when you simulate the toolpath, the tool is being normal to the surface at all times. So this
Yes.
is a simultaneous 5-axis, or also known as a true 5-axis machining.
Excuse me, Uday. I'm so sorry. I was a little ashamed for the noise. Could you explain me again about the gouge? That gouge is for avoid that the tool go down. I mean, turn for the border.
Well,
Is
to
that
check
correct?
for collision against adjacent surface, so if you want to make sure that the tool is not, cutting into any of the adjacent surfaces.
Okay, okay, okay. So that gouge helps or make sure that the tool never go out of the surface. Always touch the surface.
Yes, we said retract along tool axis, which means it may ride along the surface, but it's going to check for gouge against the tool tip, the tool shank, and also the holder. So and the gouge check, you have the options to specify, what part of the tool geometry you want to set for gouge. You can say shaft, tip, and also clearance you can specify for it.
Okay,
So
okay,
now
got
once you have this toolpath programmed in here, you could go ahead and output the G code. So right click on the machining job, and then you select post all, and we have the post processor selected in here. We want to do the shopbot as the post processor, so you would pick shopbot inch as your post processor from the list, and then post it, and your posted code would now show up. And you can see the first operation is an indexed operation at 3-axis, and then once the roughing is completed, you will see that there is a simultaneous 5-axis output in here. So you have the 5-axis output. Your M5 represents your 5-axis output. You have your X, Y, Z coordinates, and then your primary and the secondary coordinates, A and B.
I understand.
So this is
One
a
question.
simultaneous 5-axis output.
Always, yes, it's like a modal procedure. One question. If the surface is not just one, um, maybe we can let me
Sure.
minimize this, or maybe you can do it here. Yeah, okay, go ahead. Yeah, here we have just one surface, right? But what about if this, for any reason, this geometry is created by the addition of one by here, maybe another by here, another by here, three surfaces. I need to touch or select all those three surfaces in order to machine this part.
Yes, you would select them as either a drive surface or a gouge surface, depending on what surfaces you would like to machine. Now, for example, I'm going to pull in another example in here, and we'll take a look at that as well. Just give me one moment here.
So the deep of my question means exactly something like that. We have, by some reason, one arc by here and another arc by over there. There are 3 or 4 or 6 several surface. So we can, in the moment when we choose the surface for make normal to the surface, I choose all of them at the same time.
That is correct. So you can select these surfaces and program your toolpath. So in this particular case, I want to have these 3 surfaces selected in here. I generate my toolpath, and you can see that now in the animation, you're programming this particular surface. Let me slow down the simulation so I can get her.
Yeah, that was so fast. Yes. Okay.
And now you define your machine tool. I hadn't defined it as a 5-axis machine. And now when you post-process this out to ShopBot, you will notice the output in here.
And everything is M5.
M5 represents a true 5-axis motion. Simultaneous 5-axis.
Right.
So you set your primary, secondary axis, you generate your toolpath, you post-process, and there's your output for primary and the secondary angle.
Okay, now I understand.
Yeah, so you can select multiple surfaces to program your toolpaths. You can also specify your rotary axis limits in here. And then post-process it. You'll see the angle output right in here.
There is a change, exactly.
Okay?
Cool, thank you. Thank you very much.
So this is how you would basically program 5-axis toolpaths.
I have to review all these, especially the last part that was quicker than the first, but I need to, I have now a better idea about how can we set up and work with this 5-axis. I will try to, honestly, I will try, how the interface is real similar to the SolidWorks. I will try to make some modelings like you have there that you are showing me. So I will try to practice this kind of setups and create some of this operation as well in 5-axis.
All right.